The biggest and the most powerful space telescope in the world was launched by NASA a few days ago. It's named the James Webb Space Telescope. The James Webb Space Telescope, sometimes called JWST or WAVE, is an orbiting infrared observatory that will complement and extend the discoveries of the Hubble Space Telescope with longer wavelength coverage and greatly improved sensitivity. The longer wavelengths enable Webb to look much closer to the beginning of time and to hunt for the unobserved formations of the first galaxies, as well as to look inside dust clouds where stars and planetary systems are forming today. The James Webb Space Telescope was launched on 25th December 2021 and arrived at the Sun-Earth L2 Lagrange points in January 2022, which is 1.5 million km away from the Earth. The James Webb Space Telescope has a mass that is about half of Hubble Space Telescope's mass. The JWST has a 6.5 meter diameter gold-coated beryllium primary mirror made up of 18 separated hexagonal mirrors. The mirror has a polished area of 26.3 square meter, of which 0.9 square meter is obscured by the secondary support stars, giving a total collecting area of 25.4 square meter. This is over 6 times larger than the collecting area of Hubble's 2.4 meter diameter mirror, which has a collecting area of 4 square meter. The mirror has a gold coating to provide the infrared reflectivity, and this is covered by a thin layer of glass for durability. Webb often gets called the replacement for Hubble, but we prefer to call it a successor. After all, Webb is a scientific successor to Hubble. Its science goals were motivated by results from Hubble. Hubble science pushed us to look to longer wavelengths, what Hubble has already done. In particular, more distant objects are more highly redshifted, and their light is pushed from the EV and optical into the near infrared. Thus, observation of these distant objects, like the first galaxies formed in the universe, for example, requires an infrared telescope. This is the other reason that Webb is not a replacement for Hubble. Its capabilities are not identical. Webb will primarily look at the universe in the universe, while Hubble studies it primarily at optical and ultraviolet wavelengths. Webb also has a much bigger mirror than Hubble. This larger light collecting area means that Webb can peer further back into time than Hubble is capable of doing. Hubble is in a very close orbit around the Earth, while Webb will be 1.5 million kilometers away at the second Lagrange point. Infrared waves or infrared light are part of the electromagnetic spectrum. People encounter infrared waves every day. The human eye cannot see it, but humans can detect it as heat. These regions of the spectrum is divided into near, mid, and far infrared. The region from 8 to 15 microns is referred to by Earth scientists as the thermal infrared scenes. These wavelengths are best for studying the long-wave thermal energy radiating from our planet. Because of the time it takes light to travel, the further away an object is, the further back in time we are looking. This illustration compares various telescopes and how far back they are able to see. Essentially, Hubble can see the equivalent of toddler galaxies, and Webb telescope will be able to see baby galaxies. One reason Webb will be able to see the first galaxies is because it is an infrared telescope. The universe, and thus the galaxies in it, is expanding. When we talk about the most distant objects, Einstein's general relativity actually comes into play. It tells us that the expansion of the universe means it is the space between objects that actually stretches, causing objects or galaxies to move away from each other. Furthermore, any light in that space will be also stretched, shifting that light's wavelengths to longer wavelengths. This can make distant objects very dim or invisible at visible wavelengths of light, because that light reaches us as infrared light. Infrared telescopes like Webb are ideal for observing these early galaxies. Webb is designed to look deeper into space to see the earliest stars and galaxies that form in the universe, and to look deep into nearby dust clouds to study the formation of stars and planets. In order to do this, Webb will have a much larger primary mirror than Hubble, which is 2.7 times larger in diameter or about 6 times larger in area, giving it more light gathering power. It also will have infrared instruments with larger wavelengths coverage and greatly improved sensitivity than Hubble. Finally, Webb will operate much further from Earth, maintaining its extremely cold operating temperature, stable pointing, and higher observing efficiency than with the Earth orbiting Hubble. The James Webb Space Telescope will not be in orbit around the Earth, like the Hubble Space Telescope is. It is actually orbit the Sun 1.5 million kilometers away from the Earth at what is called the second Lagrange point or L2. This allows the satellite large sun shield to protect the telescope from the light and heat of the Sun and Earth and Moon. Why does the directions of the Earth and Sun matters? Wave primarily observes infrared light, which can sometimes be felt as heat, because the telescope will be observing the very faint infrared signals of very distant objects. It needs to be shielded. The telescope itself will be operating at about minus 370 degrees Fahrenheit. The temperature difference between the hot and cold side of the telescope is huge. You could almost boil water on the hot side and freeze nitrogen on the cold side. To have the sun shield be effective protections against the light and heat of the Sun, Earth and Moon, these bodies all have to be located in the same directions. This is why the telescope will be out at the second Lagrange point. What is L2? Joseph Louis Lagrange was an 18th century mathematician who found the solution to what is called the three-body problem. That is, there are any stable configuration in which three bodies could orbit each other, yet stay in the same position relative to each other. As it turns out, there are 5 solutions to this problem, and they are called the 5 Lagrange points after the discoveries. At Lagrange points, the gravitational pull of two large masses precisely equals to the centripetal force required for a small object to move with them. The L1, L2 and L3 points are all in line with each other, and L4 and L5 are at the point of equilateral triangles. The first Sun-Earth Lagrange point L1 is 1.5 million kilometers from the Earth towards the Sun, and there have been many solar observatories located here. There have been other satellites out at Sun-Earth L2 where we will be. It is easy for an object like a spacecraft at one of these 5 points to stay in place relative to the other 2 bodies, that is the Sun and Earth. In fact, L4 and L5 are stable in that objects. There will be orbit L4 and L5 with no assistance. Some small asteroids are known to be orbiting the Sun, Earth L4 and L5 points. However, L1, L2 and L3 are metastable. So objects around these points slowly drift away into their own orbits around the Sun unless they maintain their positions. For example, by using small periodic rocket thrust. This is why L1, L2 and L3 does not collect objects like L4 and L5 do. If Webb is orbiting the Sun further out than Earth, should not it take more than a year to orbit the Sun? Normally yes. But the balance of the combined gravitational pull of Sun and the Earth at the L2 point means that Webb will keep up with the Earth as it goes around the Sun. The gravitational forces of the Sun and the Earth can nearly hold a spacecraft at this point, so that it takes relative little rocket thrust to keep the spacecraft in around L2. And Webb will be orbit around L2, not sit stationary precisely at L2. This orbit is actually similar in size to the Moon's orbit around the Earth. How to communicate with Webb? Webb's position out at L2 also makes it easy for us to talk to it, since it will always be at the same location relative to Earth in the midnight sky about 1.5 million kilometers away. We can have continuous communications with it as the Earth rotates through the Deep Space Network (DSN), using 3 large antennas on the ground located in Australia, Spain and California. During routine operations, Webb will uplink command sequence and downlink data up to twice per day through the DSN. The observatory can perform a sequence of commands autonomously. Typically, the Space Telescope Science Institute will upload a full week's worth of commands at a time and make updates daily as needed.